Cheng from Stanford University. As far as I know, a student of Rick Cheng, right? And today he's going to talk about a compactness result for energy minimizing harmonic maps with raw domain metric. Thank you.
Thank you. First, let me thank the organizers for granting me this opportunity to speak here. I apologize for the long title, but if you feel like it's too long, then we don't really need this, because energy minimizing is enough to characterize the class of maps I'm interested in today. That's a joke. Let's see. Yeah, so I'll first set the stage and introduce the class of maps that I'll be talking about today, and then maybe explain why we care to study sequences of them and their compactness properties. And then I'll state our main results along with an application. And finally, if time permits, I will give a proof. So all the results I'm going to write down today are local in nature. So I'm going to assume that the domain of my maps is the unit ball in the Euclidean space Rn, which I'll denote by B. So B means the unit ball in Rn. And on this unit ball, I put some metric, which I'll describe later. Basically, it's where the roughness comes in. And the target manifold will just be a smooth, compact Riemannian manifold. Okay. And now let's talk about this metric G. So I'm going to assume that this metric G belongs to a class which I'll denote by F sub lambda, and it's defined as follows. So first of all, each component Gij of the metric is a bounded measurable function on the ball, and the metric is bounded above and below by the Euclidean metric with this constant. So specifically, that means that these two inequalities hold. That's for all vectors C in Rn and for almost every x in the ball. Okay. And you've all seen the definition of the energy this morning or early afternoon. I'm going to write it down again because I need to introduce a notation for it just for convenience. So given a map, the energy is defined by just integrating the norm of its differential squared and integrated with respect to the volume form. So the volume form and the norm here are both with respect to the metric G. And I'm going to denote this by E for energy, obviously, and then it depends on G, and it's the energy of U over the set A. Okay, that's the notation I'm going to use today. And then, just to remind you, a map from B into the target manifold is called energy minimizing if so it's energy minimizing with respect to metric G if for all smaller balls strictly contained in the unit ball, and for all comparison functions V mapping from B to N, and agreeing with U on the boundary of BRX, we have that the energy of U over BRX with respect to G is less than or equal to the energy of V over BRX with respect to G. Okay, so such maps which minimizes energy with respect to a bounded measurable metric bounded like this are the central object of today's talk. Right. So let me just briefly explain why we care about compactness results for such maps. Well, the short answer is that compactness results are closely related to regularity theory, because you see these are energy minimizers. They are solutions to a variational problem, so naturally we ask how nice they can be. And in the case where G is smooth, in quotes, the answer to how nice these energy minimizers can be is given by the classical work of Cheng and Uhlenbeck. It's 82. It's a paper in JDG. So if in addition to, if your metric, if the domain metric is, quote, smooth, I put quotes here because I didn't want to get bogged down in the specific regularity requirements, but certainly C2 suffices. So in the smooth case, if you have such a metric and U is an energy minimizer with respect to G, so energy minimizing. Then the Cheng-Uhlenbeck result says that the singular set is very small in the following sense. I'll recall the definition of the regular set and the singular set later, after I write down the statement. So it says that the Hausdorff dimension of an energy minimizing map with respect to a smooth metric is always bounded above by the dimension of the domain minus 3. So the singular set always has codimension at least 3. And now let me just open a little box here to remind you of what this means. So the regular set, I'm sorry, I just need a bigger box. The regular set of U is defined to be those points in the unit ball such that U is wholly continuous in a neighborhood of X, so near X. And the singular set is, of course, the complement of the regular set, denoted as such. Okay, so basically, in the smooth case, energy minimizing maps are regular away from a set of codimension at least 3. And this is a long theory. a lot of ingredients go into it. And some parts of it really uses the continuity, if not smoothness, of the metric. So a natural question is, how much of the Schoen-Uhlenbeck regularity theory survives if we relax the regularity requirements on G? If we only have bounded measurable metrics. And by the way, this if you don't like to talk in vague terms, then basically you can replace all the roughs in this talk by bounded measurable. Yeah, so the question is, what happens? What happens if G is allowed to be rough, if it's discontinuous? Things like that. And perhaps the first step towards answering this question was contained in the work of Xi. Goes back to 96. So he managed to generalize sort of the first step in this Schoen-Uhlenbeck theory. The result basically says that a point X is in the regular set if the energy of the map does not concentrate there. I'm going to need a full statement later, so I'll just write down the whole thing. So basically there exists an epsilon. This epsilon depends on the following things. First of all, the domain dimension, and then the capital lambda that appears in the definition of this class of metrics. So there exists such a positive number such that if G is a metric in the class F lambda and U is energy minimizing with respect to G, this, and if you go to a point and there's no energy concentration in the following sense, the lim inf as r goes to 0 of the energy at the scale r at a point x is less than this threshold epsilon. So if 1, 2, 3 are fulfilled, then x is in the regular set of U. In other words, there's some exponent alpha such that U is C0 alpha in the neighborhood of x. So a direct consequence of this, well, we usually call this type of theorem an epsilon regularity theorem. A direct consequence of Xi's version of the epsilon regularity theorem is that so let U be as above. I mean as in the theorem. So consequence of this theorem is that if you have a map that's energy minimizing with respect to a metric in f lambda, then actually the hn minus 2 Hausdorff measure of a singular set vanishes. And then, well, one naturally questions, can we improve this bound to recover the full Cheng-Uhlenbeck result? So can we push n minus 2 down to n minus 3 plus some number for all? Right, I mean, if we can replace n minus 2 by n minus 3 plus lambda for all positive lambda in this vanishing condition, then we would have gotten this conclusion. Unfortunately, the answer is, well, not yet. Well, I'd like to say, but and the thing is this. So in the original Cheng-Uhlenbeck work, this step, going from the vanishing of the n minus 2 Hausdorff measure of the singular set to this n minus 3 dimension bound, in the Cheng-Uhlenbeck work, it's done by a dimension reduction argument that goes back to Federer. Essentially, it says that if your singular set has very high dimension, then you can produce a minimizer that has a lot of translation invariance. And so you can push the dimension of the singular set down by proving the non-existence of highly symmetric minimizers. But this whole process relies heavily on having a monotonicity formula, which, when the metric is rough, I still haven't figured out how to prove, because the proof by Rick and Uhlenbeck really uses the continuity of the metric. And so does a lot of other proofs I've seen. Well, some, not a lot. And so we had no So on the one hand, on the one hand, with on the other hand, when the metric is so non-regular, it's hard to obtain the monotonicity formula. On the other hand, we also don't have a counterexample for this, so it's really, I really don't know what to expect here. And that's the main reason why in the rough metric case, we're not quite there yet. However, we managed to recover another important ingredient in this dimension reduction argument, and that's the compactness theorem. That's the main theorem of my talk today. And I have to say, although we can't use it to get this desired bound, because for lack of a monotonicity formula, still it has implications on the regularity of energy minimizing maps with rough domain metrics. So let me now state the compactness theorem. So the setting is the following. We have a sequence of maps going from the ball into our target manifold N. And they're each energy minimizing with respect to a metric in the class F lambda. So So energy minimizing with respect to some metric gk that falls into this category, f sub lambda. And then to get compactness result, we need to impose some bounds. So let's assume that the energy of this sequence is uniformly bounded on each compact subset of the unit ball. So the supremum over k of the energy with respect to gk of uk on the ball Brx is finite, and this is for all Brx strictly contained in the unit ball. Okay, suppose you have a sequence of energy minimizing maps and with local uniform energy bounds. Then there are basically two conclusions, as does any reasonable compactness theorem. So the first conclusion concerns the property of the limit map. It should still fall in the class we started with. And the second conclusion concerns the mode of convergence. So the conclusion is that there exists a map that's energy minimizing. And a map and a metric. Yeah, let me state it this way. And a metric G in f sub lambda such that the following things hold. Number one, U is energy minimizing with respect to G. Number two, up to a subsequence, we have that. First, we have weak convergence. That's just basic functional analysis. The important thing is what I'm going to write down now. So we don't quite get strong W12 convergence as Rick and Lundbeck did, but we sort of have the next best thing. There's convergence of energies in the following sense. So if you look at, again, a ball strictly contained in the unit ball, then the energy with this, the limit as k goes to infinity of the energy of uk on Brx with respect to the metric gk is the energy of the limit map on this ball with respect to the metric g. I don't think I'll have time to go through the proof of this theorem in much detail. G? It's a, yeah, there exists a G, yeah. It's a limit metric, but I'm not, yeah. Yeah, so due to time limitations, I won't be able to go into the details of this theorem too much. So let me focus on its applications. As I said before I wrote down the theorem, it has implications on the regularity of energy minimizing maps. So although we don't get a strong conclusion, we can manage to push this down a little bit. So there exists an epsilon depending on, again, the domain dimension and capital lambda involved in the definition of the class of metrics we consider. And then there is an additional parameter which will be clear, which I'll explain later. So there exists such a positive number such that if, again, G is a metric in the class F lambda and U is energy minimizing with respect to G. Then, and this last assumption is where this E0 appears. And it looks kind of unpleasant, but we sort of need it here because we can't use the monotonicity formula because we don't know. We can't prove it yet. Yeah, anyway, the condition I'm going to write down here is there for lack of a monotonicity formula. It's bound on the energy of U at all scales. And so if we have a monotonicity formula, then it would just, the energy of U at smaller scales would just be bounded by the energy of U on the whole ball, says, say. But anyway, so it says that basically for all x in the half ball and for all radius r less than a quarter, the rescaled energy of U on the ball BRX with respect to the metric G is bounded above by this number E0. So if we have an energy minimizing map with respect to such a metric and whose energy is bounded at all scales, then actually the H n minus 2 minus epsilon measure of the singular set vanishes. Okay, so it's on one hand, it's a slight improvement of what the result of the result of Xi here, because we pushed n minus 2 down to n minus 2 minus epsilon. But on the other hand, we had this additional assumption here because we don't have a monotonicity formula in the rough metric case. Let me call this assumption star. So a couple of remarks, well, just one. We don't know if this assumption star can be weakened in general, but there's one case where we can remove it altogether, and that's when the target manifold is simply connected. So maybe because right. In the case where the target manifold is simply connected, the reason why we can remove the assumption star is because there is a universal energy bound due to Robert Hart, David Kindleracher, and Pham Hoa Lin in the late 80s. So N is assumed to be simply connected in this theorem. I'm not going to write that down again. They say that there exists a constant. So if you take a compact subset of the unit ball, then there exists a constant C depending on N, capital lambda, for a target manifold, and this set K, such that if G, again, is in this class at lambda, and if U is energy minimizing with respect to G, then let's see. Yeah. Then the energy of U on this compact set, this chosen compact set K with respect to the metric G is just bounded by this absolute constant C. So this is a very strong energy bound, and it's actually much stronger than what we needed here. And so that is why in the case where n is simply connected, we can just remove the assumption star. So in the remaining time, let me talk about how we prove corollary 1, if you're still with me. I'm sorry, Rick. So as you might have guessed from the statement, from the way the corollary is stated, the proof is by contradiction. And I must say that this type of result and the structure of its proof goes way back. I think it originated with Omegren. And anyway, so let's prove this. So we suppose it's false. Then you'll get a sequence. So what we're going to do is that we're going to suppose that it's false, and we'll get a sequence of counterexamples that violates this vanishing conclusion with a sequence of epsilons that go to 0. And we will rescale the sequence of counterexamples appropriately and use the compactness theorem to get a limit map that violates Xi's result and obtain a contradiction. So if corollary 1 is false, then we get a sequence of epsilons going to 0, a sequence of metrics here, and a sequence of maps, energy minimizing with respect to GK, such that singular set, the n minus 2 minus epsilon k Hausdorff measure of the singular set is positive. And the measure we're going to work with is not, for technical reasons, is not this one, but the Hausdorff pre-measure. It's the thing we use to define Hausdorff measure. So it's not quite a measure, but it detects the Hausdorff measure. It detects the Hausdorff dimension, and it has better properties as far as our purposes are concerned. So I'll assume you know what this means, because I don't. So just by standard measure theory, which you can find in Leon Simon's book, you can pick points in a half ball and very small scale, such that basically one good property of this measure compared with this is that you can find points of density where density is bounded below by a definite constant, positive constant, that helps you when you pass the limits. just by standard measure theory, we can find points and radii such that this density ratio is bounded below by a constant that does not depend on k. And then these two parameters tell you how to rescale your maps. Yeah. So we define a new sequence of maps called VK, which are defined as follows. And a sequence of metrics out of the GKs as follows. And it's easy to check that the sequence HK is still in this class, and VK is energy minimizing with respect to HK. Moreover, by the way the energy rescales, the energy with respect to HK of VK on the whole ball is just this thing. Which is less than or equal to E0 by our assumption here. That is why we needed this assumption. And moreover, we have a straightforward computation shows that the following is true. Anyway, now you see that the assumptions, I erased it. The assumptions of the compactness theorem are verified on the sequence of maps and the sequence of metrics. So you can invoke theorem 1 to get a limit map that's energy minimizing with respect to a metric H here. Now, I'm almost done. Now it's Xi's theorem, the epsilon regularity theorem, which I erased. And the convergence of energy conclusion in the compactness theorem tells you that basically singularities cannot disappear. So I claim we have the following. It's epsilon regularity plus convergence of energies. I'm just referring to conclusion 2 of the compactness theorem. Implies that the limit sup of these things is less than or equal to basically the measure basically in very rough terms the size of the singular set is upper semi-continuous with respect to the mode of convergence stated in the compactness theorem. This k goes to infinity. However, each term in this sequence is bounded below by a positive constant that does not depend on k. So in particular, this limit sup is strictly bigger than 0. So equivalently, as I said, this Hausdorff measure with infinity here detects the Hausdorff dimension. So this is equivalent. So the positivity of this thing is equivalent to the positivity of the usual n-2 Hausdorff measure. However, V is an energy minimizing map with respect to a metric in here. And so according to Xi's theorem, the HN-2 measure of the singular set must vanish, and that's a contradiction. And so that's how we get the corollary. And I'll stop here.
Any question or comment? So, okay, let's end the game. Cheng, thank you.